Hello everyone, I'm honored today to be a part of the first international conference on physical and engineering sciences. I'm Nasri and Houda, second year PhD student at Ismail University of Meknes. Today I'll present to you an orthogonal two-port MIMO antenna for 5G application, a work done by myself with the collaboration of both Professors Mohammed Ghzaoui and Mohammed Fattah. In the context of preparing my PhD thesis, Contribution to the study of MIMO antennas for future 5G wireless communication systems. As a starter, I'll present to you the layout that will be followed during the presentation. I'll start with a small introduction, then I'll enumerate some of the MIMO advantages, then we will discuss both the design and the results of the antenna, to end with a conclusion. It is only 40 years since the birth of mobile telephony, but the development of cellular network has been at a pace which has fueled both social change and innovation at a global scale. The capabilities of 3G and 4G networks were developed in response to demands for a mobile internet. However, the inexorable rise of IoT and demands of emerging applications such as AI, AR, and automated cars have stretched the 4G capabilities, which led to the development of 5G. When we talk wireless communications, the most crucial components to be mentioned to ensure it are antennas. They play an important role in the operation of all wireless components. However, antennas that are specifically designed for 5G need to have new design and specification to meet all the new band's requirements. There are different types of antennas, but MIMO are the best to use for better and efficient results. Now we'll move on to the MIMO antenna advantages. We will start with a brief definition of MIMO antenna. MIMO stands for multiple input, multiple output. Essentially, it allows multiple streams over the same data channel. MIMO has many advantages, but here we will mention the three main ones. Beam steering. One of the major problems in wireless telecommunications is interferences. The beam steering is a technique that permits to get rid of them. It makes the antenna control the signal transmitter over multiple antennas in a way that the energy is focused on a single user. It helps us get rid of the problem of RF multipath. Next, we have spatial multiplexing. On the other hand, this technique adds data carrying on the same bandwidth, which increases the data rate according to the Shannon-Hartley theorem. At last, we have diversity. Diversity is a method that allows each signal to be encoded properly. The aim of this is to permit to each signal to adapt to each channel by compensating losses and adding noises, meanwhile adding redundancy that will correct bit errors, which guarantees a crucial requirement for the fifth generation. Now that we've discovered more the advantages of the MIMO antenna, let's discuss the main thing in this presentation, that is the antenna design. As we can see, the design is simple. It's a patch antenna with two ports. It is simple to fabricate. The proposed antenna covers the band from 24.29 GHz to 26.84 GHz. It's a band that's been commercialized since 2020 in Europe. The bandwidth of the antenna is 2.55 GHz and her peak gain is 6.5 dBi, which are largely sufficient for the use in 5G applications. Let's discuss more the specification of the antenna we saw previously. The antenna is orthogonal, it has two ports, it is millimetric on a scale of some millimeters, which is very convenient, it is very, very small. We use the Roger RT duroid substrate material, which is very affordable comparing to other materials. It has a very good dielectric permittivity of 2.2. We fed the antenna using a microstrip line, and the width of the microstrip line used is very small. Let's discuss more what makes the antenna more interesting. When we want to analyze an antenna, we have some parameters to check to make sure that the antenna is performant. We've used HFSS to do so, and it stands for High Frequency Simulation Software. It is an electromagnetic simulation software for designing and simulating high-frequency electronic products. In our case, they are antennas. First parameter to discuss, and the most important one, is return losses. In this case, we have two values, S11 and S22. The return loss has to have a value under -10 dB on the band required. Here, we have a very good result. The S11 and S22 have reached -55 dB and -35 dB respectively, which is very good and very promising. Next, we will check the S12 and S21. They are transmission coefficients. They have to be largely under -10, which is very the case, and we can check that the maximum that they reach is in -32 dB in the wanted band. We have next voltage standing wave ratio. With this ratio, we check the reflection of the antenna, how the antenna tolerates the power received. For a good ratio, we have to have a VSWR equal to 1, which is very obvious on the figure. It is very good. It is 1 for both VSWR1 and VSWR2. Last, we will check the radiations, E-plane and H-plane. With a center frequency of 25.65 GHz, both radiation patterns show the proposed antenna has a minimum back lobe in the chosen band, which is required to guarantee the performance. To sum up our presentation, we saw that the proposed antenna has a very simple design and very, very affordable. It can be easily fabricated. It has very advantageous results for the studied frequency band, the 26 GHz, that is very commercialized lately. The antenna is very promising for the 5G application, either for its performances and its results, or for the size. It is very small to be integrated in devices that we use in our daily life. Thank you.